In this video, we will look at a problem involving free fall and see how we can apply the principles of problem solving in kinematics. The problem states that someone is standing on the edge of a cliff 42.7 meters above the valley floor. They toss a ball straight upward with an initial velocity of 22.5 meters per second. We can neglect air resistance and consider the ball to be leaving from the cliff itself. How high above the valley floor does the ball get? Is our first question. Then we say the person does not catch the ball when it comes back down and it falls down to the valley below. How fast is it traveling just before it hits the ground? Well, it's always helpful for us to draw a diagram of the situation showing the motion of the object, and that's what we have here. We've also put some information into this diagram, but it's always a good idea to construct a data table. Remember, in kinematics, there are primarily 6 variables: initial position, final position, initial velocity, final velocity, acceleration, and time. The first thing that we are asked is how high above the valley floor does the ball get? And therefore, we will only concern ourselves with this part of the trip, right? The trip that gets us to the highest point, to answer the first question. And so we assemble the data here for the trip up, because step 1 is to read the problem and determine what the problem is telling you. In this case, we are told that the initial position is 42.7 meters. That's our position here at the top of the cliff. The final position is the height, which is what we're trying to find in the problem. The initial velocity is plus 22.5 meters per second. Notice I've taken pains to put the plus sign there to signify that the initial velocity is upward. The key to solving this part of the problem is to realize that at the peak of its motion, for a brief moment, the ball has a 0 velocity. It was moving upward a moment before. It'll be moving downward a moment from now, but right now it is at a velocity of 0. And so if we only consider the trip up, that means the final velocity is going to be 0. Since we are neglecting air resistance, the ball is in free fall, and so we know that its acceleration is 9.80 meters per second squared, down, and we signify that by putting a negative sign. In this problem, up is going to be positive. We do not know the time it takes for the ball to go up. Right, so we have examined the problem. We have determined what the problem is trying to tell us. Step 2 is to determine what the problem wants us to find out. Right, that is going to be this right here, the final height on the trip up, the highest point that we reach, and we're just going to call that h. Now, there are 2 ways to solve this problem, and both of them hinge on the third step in the process, which is to determine what is irrelevant to the problem and then use that to guide you to the proper equation. In this case, what is irrelevant to the problem, if we wish to solve it in one step, is time. So if we want to solve the problem in one step, we can turn to the equation of kinematics that does not involve time. And it's this one. V final squared equals V initial squared plus 2 times acceleration times x final minus x initial. Right, so in this case, the final velocity is going to be 0. The initial velocity is 22.5 squared, and that is plus 2 times the acceleration, negative 9.80. Very important to put that negative sign there, or you're not going to get the right answer. And I'm just going to call x final minus x initial delta x for now. Taking this over to the other side so that it becomes positive, we get this. 19.6 times delta x equals 22.5 squared, which is 506.25. Solving for delta x, we get 25.8 meters. Notice, though, that's the change in position from the top of the cliff to the highest point. We are specifically asked for the height above the valley. Right, and so that height is going to be 42.7 plus delta x, and that's going to give us a height of 68.5 meters. So by examining which of the pieces of data is irrelevant, not given, not asked for, irrelevant, we were able to solve the problem in one step. Now it is, of course, possible to solve this in 2 steps, if you wish. One method is not preferable to the other, it's just the one-step method is faster. The 2-step method first involves finding this time. How long does it take for the ball to reach its highest point? For that, we utilize the first of the kinematics equations. V final equals V initial plus acceleration times time. Again, for the trip up, the final velocity is 0. The initial velocity is 22.5. The acceleration is negative 9.80, and the time is t. Solving this equation for time, we get the time up, which is 2.30 seconds. Now, with that time in place, we can use our kinematics equation of position to find the final position. X final equals x initial plus the initial velocity multiplied by the time plus 1/2 times the acceleration multiplied by the time squared. That final position is h. The initial position, remember, is the height of the cliff, 42.7 meters. The initial velocity, 22.5. The time up, 2.3. The acceleration is negative 9.80, very important, and the time squared. Calculating all this out, we get a height of 68.5 meters. And so, whether we do it in 1 step or 2 steps, we get the same answer, which is certainly reassuring. Now, the second thing that we are asked here in the problem is, how fast is it traveling just before it hits the ground? In other words, what is the final velocity of the ball down here? Well, now we create another data table. This time, a data table for the total trip from here to here. And so in this instance, the initial position is 42.7 meters. The final position is the ground, which is going to be 0. The initial velocity is going to be 22.5 meters per second. Once again, I have the plus sign to signify that it's upward. The final velocity, we do not know. In fact, it's what we are being asked to find. The whole trip, up and down, the ball is in free fall. Whether it's going up or going down, it's in free fall. We neglect air resistance, and so the acceleration is still negative 9.80 meters per second squared. And the total time in the air, this is not something that we know. So once again, we write out what we know, what the problem tells us. We identify what it is we need to find. And then, if we wish to solve the problem in 1 step, we take a look to see what is irrelevant to the problem. Once again, in this problem, the total time in the air is not given. It is not asked for. And so it's irrelevant to the problem. And so, once again, if we wish to solve the problem in one step, we can go to the kinematics equation that does not involve time. And just as we did before, we can plug in values to this equation. We are looking for the final velocity. The initial velocity is positive 22.5, and the acceleration is negative 9.8. Now this delta x is going to be the final position, 0, minus the initial position, 42.7. It's very important to have those in the proper order, or you're going to get an incorrect answer. Because the displacement of the ball is, in the end, 42.7 meters downward. It goes up for a little bit, but then it comes down, so that the total displacement from the initial position to the final position is going to be downward negative. Performing the calculations, we find that since we're taking the square root, we have a choice between the positive and the negative values. The velocity is downward, and so we choose the negative value, negative 36.6 meters per second. Remember, that negative sign is one of the two options we get because we take the square root. We choose the negative sign because the final velocity is downward. Just as before, it is entirely possible to solve this problem in 2 steps. It is a little more difficult because we have to calculate the total time in the air. Here's one way to do it. We know that the time up is going to be 2.30 seconds, which we determined in the earlier problem. Now we need to figure out the time down. And we can get that based upon the work that we did before. We can look at the trip down and say the final position equals the initial position plus v naught t plus 1/2 a t squared. Looking now at the second half of the trip, second part of the trip, from the highest point down to the ground. That final position is going to be 0. The initial position is the height we got before, 68.5 meters. The initial velocity, well, it's the velocity here at the peak, which is 0. And, as always, in free fall, the acceleration is negative 9.80. We take this over here so that it becomes positive. We get 4.9 t squared equals 68.5, and that tells us that the time down equals 3.74 seconds. So the total time in the air is 6.04 seconds. Once we have that time in hand, it's now a simple matter of using the first kinematics equation to find that final velocity. But we have to be careful. We have to remember that the initial velocity, 22.5 meters per second, is upward positive, and the acceleration in free fall is downward negative. It's very important to keep those signs straight. Otherwise, you run the risk of making a significant error. This gives us a final velocity of negative 36.7 meters per second. Again, the negative sign indicating that the velocity is downward. These two numbers are very close. They only differ in the final significant digit. And so we can attribute that very small difference to rounding error. So once again, whether we take it in one step or two steps, we get the same result.